So far we have learned that in supervised machine learning, we have a data set D, which is a set of m data points, xj and yj, where j goes from 1 to m, where each of the xj is an n-dimensional real vector, and each of the yj is a scalar, a real scalar. So from now onwards, we'll represent the jth input data sample as x superscript j and its corresponding target as y superscript j. So in this in the supervised machine learning, we have a function mapping f, which is parameterized by some learnable parameter w, that maps each of the x to the corresponding y values. So in this particular lecture, we are going to learn a specific class of functions known as linear models. So in the linear model, the function f is a linear function of its input. So in the linear models, we'll have a function f that is parameterized by some variables w and b. Both are some learnable parameters. It takes an input x and it produces the corresponding y using this equation. It's a weighted sum of its input plus some bias. Where b is a bias, it's a scalar. And the w is a vector, it's an n-dimensional real vector. So this kind of functions are known as linear models because you can see that the function f is linear in its input x. It also happens to be linear in the learnable parameter w and b, and that's why we call it linear regression. So we can write this equation more compactly as f parameterized by some learnable parameter w and b takes in the input x, the jth data sample, and it produces the corresponding label yj using the equation w transpose x j plus the bias term. So this is specifically to be mathematically correct. This is an affine model where the function f is w transpose times x plus some b. If b is not 0, then this is an affine mapping. If b is 0, then this becomes a linear function. So as you can see that this function is linear in both in a learnable parameter w and b. It also happens to be a linear function of the input data samples, and often it's we can construct a very simple example where this kind of representation is not a good representation. So oftentimes what we do in machine learning, we have what we call a basis function or a feature function, which is represented by phi. So it takes an input data samples xj and it produces a new representation for our input variables. So rather than learning the functional mapping directly on the input data samples, we learn the functional mapping on some nonlinear representation of the input data samples. For example, to understand this better as to what we are doing, let's consider a simple example. So let's assume that x is a scalar. This is x-axis and this is y-axis, right? So let's assume that we have data samples like this. So here we can see without any knowledge about the function that is generating this data, or the distribution that is generating this data, we can see that this is definitely not, the y is definitely not a linear function of x. And if we try to fit a linear model, the one where the function maps directly where the function f is a linear mapping of the input data points to y, then this will simply become, in case of a scalar x, is wx plus b. And as you know, here w is a scalar and b is also a scalar. And this is an equation of a line. So different values of w and b are going to give us different lines. For example, we can have this representation, we can have this line, we can have this. So depending on the values of w and the offset b, we'll get different lines. But as you can see, none of these lines actually explain the data. None of them are actually capable of capturing the semantics of the data, right? So what if we use a new representation? For example, instead of using wx plus b, we can have a nonlinear representation of our input data samples. So let's assume that we have a function phi which takes in the input data point x, and it produces a new representation for our input data samples. So let's assume that the new representation is, assuming that the x is scalar in the same case, we are considering this data set as of now. So let's assume that this phi maps this x to x and x square. So now we can fit this functional mapping. Instead of directly mapping x to y, we can map phi x to y. So now our function changes to f of w comma b, where w belongs to R2. It's a two-dimensional real vector, and b belongs to R. Right. So in this case, our function mapping changes to w transpose times phi of x plus b, which equals w1 x1 plus w2 x2 plus b, where x1 is x and x2 is x square. So effectively, by changing the representation, we are now learning a new function, which is w1x plus w2 x square plus b. And now, as you can see, we can fit this function to a data sample, and perhaps we'll get a fit like this, given that it's a quadratic function, right? So as you can see, by just changing the representation, which forms an input to the function f, we are able to use the same linear models. We are able to capture the semantics of a data which is non-linear in nature, right? So in machine learning literature, this function phi is known as basis function. It is also known as the feature function. So it takes in the input data points. So phi is generally a mapping from an n-dimensional real vector to some k-dimensional real vector. And for the sake of simplicity in the lectures, we'll just assume that both x belongs to Rn, and also phi of x belongs to some n-dimensional real space. Because this n is a variable, so it doesn't matter. We can just represent this n by some k. And now, from now onwards, we'll assume that instead of learning the functional mapping directly on x, we'll just learn a functional mapping on phi, which we can just assume that it's an n-dimensional real vector. That is, phi belongs to R of n, right? So, in a nutshell, what we have done so far is that in supervised machine learning, we'll have some data set D, which is a set of n data points, xj and yj, where j goes from 1 to m. And for the sake of simplicity, we can just assume that each of the xj is also n-dimensional vector. Or you can just say that it's a k-dimensional vector. Just to explain you, let's say it belongs to k-dimensional space or real space, and yj belongs to real space, it's a scalar. We'll use a functional mapping or a feature function or a basis function that takes an input data point and it maps it to a new kind of a representation. And then we'll learn a functional mapping f, which is parameterized by w and b, which will take in the input as the basis function on the input data points x, and it will be phi of x transpose times w plus b, which is giving us the target y values for these x's. So by using this basis function, as we have seen in the previous example, even when we are using linear functions that are linear function of the inputs, we are able, using the basis functions, we are able to capture the data sets that are usually non-linear, as you can see in this example. So now in the rest of the lecture, we will teach you how to compute the parameters w and b, so that we can learn this functional mapping that maps the input data points to their target values.